So, good morning, all of you. Hope I am audible to all of you.
Good morning, ma'am.
Yes, ma'am.
Good morning, ma'am.
So, yesterday we saw crop synthesis, then we saw interaction of radiation with matter, in which the main, the question that may arise is what is the electromagnetic spectrum of light, starting from gamma rays to radio waves, then how that is used for your uh, chemical analysis, and what are the transitions taking place in the matter when the matter is irradiated with those light. Then we saw polymers, and polymers, half of the portion I have already given you in your assignment. That is very simple preparation from monomers, properties and application of some commodity polymers was given to you. So considering that if you write it, then things are clear for you. So understanding the rest of the part now in this PPT also, like I find it is not very specific one, like lot of general information is also given. So still, because these are common PPTs prepared by different faculty members, it is necessary for us to cover the whole portion. Okay, now one of the favorite question on polymer is the tacticity part, how the groups are placed on the main linear chain, and according to the placement, you classify them as isotactic, syndicotactic, and atactic. And then what are the examples of these polymers? Like the examples are given here. Atactic polystyrene, then polypropylene is largely isotactic, and then like what I know is your gattapacha rubber gattapacha rubber is a syndicotactic one. Okay, then yesterday we today is what date? Today is 25th. Okay, so I think this is the new slide that we should discuss. Now here we see there are certain thermoplastic resins, and there are some thermosetting resins. So what is a thermoplastic polymer and a thermosetting polymer? Now in thermoplastic polymer, like if you apply some heat, I'm telling you the main features. If some heat is applied, that heat is sufficient to break the van der Waals or intermolecular forces of attraction. So there are some intermolecular forces of attraction which holds the polymer molecules together. Whereas in thermosetting polymer, the thermosetting polymer is generally formed by condensation polymerization, and you will see that it is completely bonded with covalent bonds. Now, if there are all covalent bonds, then there is hardly any space for the intermolecular forces of attraction. And that is why when you heat a thermosetting polymer, yeah, there is some noise. Okay. So, uh, because all are covalently bonded, you will find that when you apply heat, the heat is not sufficient to melt it. Whereas thermosetting polymers, like the intermolecular forces, like this is one molecule which is green in color and one is red in color. So there will be forces of attraction between these molecules, right? So that those forces will break and the molecules will move apart. The moment they move apart or get crumpled, you get a liquid polymer or a soft gummy polymer. But when you apply heat to a thermosetting polymer, which is formed by condensation polymerization, you don't get such thing. And rather, you find that at a very high temperature, it will finally decompose. The covalent bonds will break and it will decompose to carbon dioxide and water vapor. So rest of the things you can read here. Like the thermosetting polymers are some arranged. Um, they show viscoelastic properties. Then elastomers are having entangled snarls. The molecules are entangled like this, going up or like this they'll be. And duromers are the ones which are having cross-linked structures. Okay, highly cross-linked structures. Then thermoplastic, it will melt. You can recycle and reuse, whereas thermosetting, you cannot recycle and reuse. Then thermoplastic, again, these are used for such Tupperware and decorative articles, and number of like PVC. You must have seen pipes and tubes are there that can be used. So thermoplastic polymers can be softened when heated and hardened when cooled, and that is why it can be recycled and reused. Then your thermosetting polymers are like bakelite, the handle of your knife, pressure pans, and other things, because it is you have written an assignment on phenol formaldehyde. So initially it leads to like your phenol formaldehyde ratio. If it is less than 1, then it leads to formation of novolat. And if the phenol to formaldehyde ratio is more, then you get some resol. And finally you get bakelite, which is having CH2 group in between two phenolic groups. Okay, so this is the distinguishing features of thermoplastic and thermosetting polymers. Coming to elastomers, the polymers can be easily stretched by applying small stress and regains their original shape when stress is removed. The most important example of elastomer is a natural rubber. The molecular structure of elastomers can be imagined as spaghetti and meatballs. Okay, structure. With the meatballs signifying cross-linked, or the place where it is cross-linked. Okay, so the cross linkage ensure that the elastomer will return to its original configuration when the stress is removed. Okay, then you have fibers. Fibers like have strong intermolecular forces between the chains, like they are held, like you can see a dotted line here. So they are termed as hydrogen bonding with an electronegative atom. So H bonding is there. So because of strong intermolecular forces between the chains are closely packed, giving them high tensile strength and less elasticity. Therefore, these polymers can have sharp melting points. Therefore, these are used in making fibers. So, like your nylon 66 or uh, in the nylon 66, the carbonyl oxygen and amide halogen can hydrogen bond with each other. That we have already seen. Then other parameters of classification are crystallinity. Either you may be having a crystalline polymer or amorphous. Amorphous means the molecules are randomly arranged. In crystalline polymer, the molecules will be arranged systematically with respect to each other. By backbone atom, like there can be organic or there can be inorganic polymers, like inorganic, like siloxanes, titoxanes, titanium polymers, and siloxanes, SiO2 or silicon polymers. And then structure property relationship of polymers. The macromolecules show a wide range of properties which are quite different from those of respective mode of us. They may be elastic or rigid, hard or soft, transparent or opaque, have strength of steel but can have very little lightweight, soften on heating, or can set to a hard mass on cooling the melt. These properties may vary from one type of polymer to another type. So these are some of the like fundamental parameters which influence structure property relationship. Is first is the molecular mass. Now, when I say molecular mass, if you are having a long, what you say, if you are having a polymer whose one molecule is this long. Okay, so the other molecule which will be same, if the forces of attraction is like this, then you find another polymer which is a shorter one, will have one, two, three, four, five, six forces of attraction. But this molecule, each molecule will have a large number of intermolecular forces of attraction, and therefore, if the molecular mass is high, then the polymer will be having better structural properties or better resistance to abrasion or hard and tough it will be. Then polarity. If you are having one polar group on one side, then what you will see is the intermolecular forces of attraction can be better. Like this is say a larger Cl group. So this will exert better intermolecular forces of attraction, and such a molecule will show a higher fusion point. Then molecular cohesion, then nature of polymeric chains and the stereochemistry of the molecules. All these things will govern the properties like tensile strength, crystallinity, elasticity, resistance to chemicals, wear and tear. Okay. So chain length. Coming to chain length, increasing chain length tends to decrease chain mobility, increase strength and toughness, and increase the glass transition temperature. So what is meant by glass transition temperature? It is the temperature at which a polymer or any substance moves from a very hard brittle form to a soft gummy part, or it becomes soft, doesn't lose its dimension, but it becomes soft. So this is a result of increase in chain interactions such as van der Waals attraction and entanglement that come with increased chain length. These interactions tend to fix the individual chains more strongly in position and resist deformation and matrix breakup both at higher stress and higher temperatures. Then you have branching. So greater the branching, more is the like strength. Okay, so it will become rigid, more and more rigid if branching increases or cross-linking increases. Then chemical cross-linking. Cross-linking tends to increase the TG and increase strength and toughness. Cross-linking consists of formation of chemical bonds between the chains. So, like if you see, like vulcanization of rubber is one of the example. Then car tires, for example, are highly cross-linked rubber material, as I told you in the very first beginning. Then chemical resistance. Now the polymer which are having polar functional group are like you see chemical resistance to polymer depends upon chemical nature of monomers and their molecular arrangement. As a general rule of dissolution, like materials attract and unlike materials repel. Thus, a polymer is more soluble in structurally similar solvent. So, it is soluble if a polymer contains polar functional group, it will dissolve in or swell in polar solvent. If a polymer is having non-polar functional groups, then it will swell or dissolve in non-polar solvents. Then general rules of polymer solubility. Like dissolves like. Okay. Polar solvent, polar polymer will dissolve. Non-polar solvent, non-polar polymer will dissolve. PVA will dissolve in water and polystyrene in toluene. So as the molecular weight increases, solubility of polymer decreases. And when the molecular weight increases, the rate of solubility decreases. Then cross-linking eliminates solubility. Okay, so that is equilibrium phenomena. Crystallinity needs strong covalent, strong solvent to eliminate crystalline bond. That is, can also be done by heating towards crystalline melting point. So this is yes, polymer crystallinity. Okay. So what is crystallinity? Like a very specific arrangement of molecules with respect to each other, means they are aligned in such a way that they have very nice stacking, one after the other. Like you can see, this is the crystalline region, and this is the amorphous region having such kind of thing. So polymers are rarely 100% crystalline because the non-crystalline part will hold it together. So this is the crystalline region, and difficult for all regions of all chains to become aligned. So degree of crystallinity expressed as percentage crystallinity. Some physical properties depend on the percentage crystallinity. So heat treating causes, or heat treatment causes the crystalline region to grow. Just like you give annealing to a metal, the polymers are given some heat treatment so that the crystallinity increases, or the percentage crystallinity in that polymer increases. And depending on where you are using, it is then treated. So this is amorphous region is shown here like this, entangled stars. Then the crystal nucleus is here, and the time molecule, like which is moving, like this is the crystalline part, and the molecule which holds these together is termed as the time molecule. Then laminar fibrils, these are the laminar fibrils in a crystalline spherulite. Then crystallinity. This is ordered crystalline polymer. This is amorphous random material. And then semi-crystalline will be both random as well as crystalline like this. The between part is crystalline, the end parts are amorphous. So some highly crystalline polymers are polypropylene. No, highly crystalline polymers like polypropylene it will be available in all phases. So you have to treat it in such a way that you can get a polypropylene which is having high crystallinity. You see, polypropylene is otherwise amorphous. Okay, so you may have amorphous, you may have a crystalline polypropylene. Then syndicotactic polystyrene, then nylon, Kevlar and Nomex and polyketones. These are highly crystalline. Some highly amorphous polymers are polymethyl methacrylate, um, atactic polystyrene, polycarbonate, polyisoprene, then polybutadiene. Okay, so these are some of these. So polymer structure and intermolecular forces of attraction. Now you can see here, this is polystyrene. Okay, initially the monomer was like this, and when you brought about polymerization, one of the pi bond broke, and this has made available like this. Now this is not having any heteroatom in it. So if it is not having any heteroatom, there won't be any intermolecular forces of attraction. So rather, this a bulkier like a phenyl ring will keep the molecules apart. Like you can imagine, if the second layer is here, the third layer will be here. Every time this is the chain and this is your bulkier part, right? So this keeps it away, and that is why the fusion temperature of polystyrene is somewhere 80 degrees centigrade. Okay, uh, I don't know whether it is written here or not. So that is regarding polystyrene. Then if you see PVC will have little higher fusion temperature because polyvinyl chloride will be having, like this part is already there, Cl will be there. So the chloride part will have attraction, and that is why it will have little higher fusion temperature. The sliding capacity of one molecule over another is restricted in PVC compared to polystyrene. Okay, so this is linear polyethylene, then branch polyethylene. Then intermolecular forces will go back. So this is what we have discussed. Then the next part is, there are two kinds of polystyrene, atactic and syndicotactic. The structures are shown here. I think this we have already discussed earlier. So syndicotactic polystyrene is very orderly, um, with phenyl groups falling on alternating sides of the chain. This means it can packed very easily into crystals. So, like it will be more crystalline in nature than this particular thing. Then this is linear. Now linear polyethylene. Now you know that polyethylene bags are used. So how soft they are. The softness of polyethylene is because the molecules of polyethylene are something like this. And when you fold the polythene bag, the molecules can slide over it and move to other place, and that is why the polyethylene material will be soft, whereas your PVC chain will have Cl atom at this end. So PVC pipes, you must have seen those gray or blue colored pipes used for electrification and this thing. So it is a little rigid. It is not flexible like polyethylene. And if you go for branching, if you branch it, then the flexibility is still lost. So your agricultural pipes and all made up of high density polyethylene, black colored pipes you must have seen in the agricultural field nowadays. Lot of them are used for irrigation purpose. Okay, so intermolecular forces can be big help for a polymer if it wants to form crystals. Okay, a good example is nylon. So here you can see a nylon 6,6, and that is there. Then properties of polyethylene as a function of crystallinity. So as you go on in increasing crystallinity in polyethylene, you will find melting point. Generally, for polymers, we say fusion point or softening point and not the melting point, because some of the polymers will not show a sharp melting point. Okay, they will show a softening temperature or fusion temperature. So here, if 55% crystallinity is there, 109 is the temperature. If the crystallinity is going on increasing from 55 to 85, the melting point or the fusion temperature has gone up to 133. Okay, and accordingly, the rest of the properties. So the most important part is here, and you see that the density from 0.92 to 0.96 it has gained. Okay, stiffness 25. It was so soft and flexible that you could fold the polythene bag. Now has become 165. Okay, yield stress from 1700 it went to 5100. Okay, so glass transition temperature. So what is glass transition temperature? It is the temperature at which a hard material becomes soft, rubber sort. That is meant by glass transition temperature. Okay, a glassy state is hard and brittle state of material uh, which consists of short range vibrational and rotational motion of the atoms in polymer chain. Now here it is shown, this is the glassy state and this is the rubbery state. Now it is the reverse case. From the rubbery case it is going to the glassy state here. But generally your synthetic polymers, if you have a block of synthetic polymer and if you heat it, on heating you will find that it becomes fuse and plastic, uh, soft gummy polymer you get. So that temperature at which you are getting this conversion from hard and brittle to soft and plastic is termed as glass transition temperature. Then melting versus glass transition temperature. Now what we see is what factors affect the TM, that is melting point, and TG, that is glass transition temperature. Now both TM and TG increase with increasing chain stiffness. Chain stiffness increased by bulky side groups, polar groups or side groups, double bonds or aromatic chain groups. Okay, so here we can see a crystalline solid shows a melting point, but there is no like there is the slope of the curve is not changing at any temperature. For example, TG. So there is no TG shown here. It will directly melt, but rest of the material will show a TG where it becomes fusion plastic or soft and gummy, and then it will melt at this point or this point. Okay, so that is there. Then polymers are different. So you have different polymers like some solid crystalline and solid glassy, some crystallization and some glass transition is shown. Okay, here a semi-crystalline state can be there or a glassy solid submaterial can be there. So in such case, your TC is like this is your solid and this is the liquid part and this is the transition temperatures. So temperature at which it shows transition from this to this place, from this to that place. Here, the crystalline solid phase is here. It shows a TG, an amorphous polymer will show a TG. Then the melting point, and what you find here is it will show like the state changes, and here it will be like this, and here it will be like this. So such kind of thing. Okay, so glass transition temperature. A polymer mostly amorphous, crystalline, or in between. Also, what is glass transition temperature? The TG of a rubber band is below room temperature. The TG for of a polystyrene is above room temperature. So that is seen. So rubber is an amorphous polymer, so that will show TG below room temperature, whereas a polystyrene crystalline polymer shows TG above room temperature. So that itself is um, clear from the um, crystallinity. Okay, normal crystalline material, either crystalline or amorphous at a particular temperature, melt at a sharp, well-defined temperature. Crystalline polymer, never 100% crystalline, they are never 100% crystalline, melt over a range of temperature. Then coming to the molecular weight, like as the molecular weight increases, the nature of your material goes on increasing. Like your methane is gaseous, then ethane is also gaseous. Then as you go ahead, you get petroleum ether, then your gasoline, and then kerosene, solvent naphtha, then heavy oil, and then finally after heavy oil, asphalt or coke is there. So this is the log of modulus of elasticity versus temperature. You find that this is the rigid part, then this is the leathery part, the rubbery part where a long necking is there, like, and then this is the viscous part. So morphology and thermal mechanical properties of polymers are shown here, like all your hard and brittle polymer will be showing something like this. There is no breaking. For a small stress, your rubbery polymer, if you apply small stress versus strain, this is strain and this is stress. So you will find that for small, like you pull the rubber band with your hand, it will stretch a lot, and then it will break here. So this is the break point. Then if you are having some fibers, they also will stretch a little, and here it will break. Then you have a hard and the thermoplast are there. It will show something like this, and your very hard and brittle polymer, they will not elongate at all, but they will, like, you go on increasing the stress at a very high stress, it will directly break, so it will not show any elongation. So this part is the elongation part, and then it is breaking. Fibers will show such kind of behavior, thermoplast will show such behavior, and rigid and high impact polymers will show such kind of behavior. So that is what the stress strain curve for different amorphous, semi-crystalline polymers, and these are there. Okay. So addition and condensation polymers, their example, and this thing is given, you can read that. How strong is the polymer? How much can you stretch it before it breaks? that is given by the stress strain curve, or the tensile strength also can tell you. So the tensile strength is a measurement of the force required to pull something such as rope, wire, or structural beam to the point where it breaks. So the tensile strength of material is determined by tensile, like you go for tensile strength determination. Longer chains make stronger polymers that we have seen. The intermolecular forces of attraction will be more. Then here is your stress versus strain, and what you find, a linear elastic deformation is seen when you apply stress to some extent, then it turns like this. So there is, at this point, there is non-linear elastic deformation. This is termed as the yield point, and this part from here to here, when it is elongating, it is termed as necking. That is, for a small change in stress, you are getting such long elongation from here to here. The elongation is taking place. So that property is termed as necking, and then it breaks here. Okay. So this is how, when you apply force on both the sides, it will start becoming thin at the center, and finally it will break after certain stress. So here it is shown like this is original one. You are applying stress, making it move apart. Rather, you can think that it is something like this, elongated. A little elongation is there because it is moving from here to here. So a little elongation is there, and from here it starts becoming thin, thin, and thin, and further it goes on elongating. The thinner part goes on elongating. You can see the length of this thinner part. Here is the maximum, and that at this point it will break from here. Okay, tensile response, brittle and plastic. You can, like, this is regarding the uh,
Ma'am, if we increase that thinner part, then to thick, ma'am.
yes.
If we make it thicker, then
No, I'm not getting you. If we,
make it thicker, ma'am, from the middle also.
hmm,
Then after a lot of time, it will break, ma'am. At
if
this stage.
you if you pull it from middle,
If we make it, ma'am, more thicker, ma'am, from the middle.
yeah, whenever you apply any stress on these two sides, the force is on the opposite sides like this. So the it will be at the middle. It is going to become thin and thin because the molecules present inside this polymer material are being stressed in such a way that at the end there won't be any much deformation. But the molecules which are present at the center, they experience the stress, and due to that the molecules they get like separated, or they get aligned rather in this fashion. If they were present as such type of entanglement, then they are getting stretched and straight just like your rubber band. Okay, and they become more crystalline at this part, and the time comes that it will break here. So that is the stress strain curve. Okay. Okay, so the onset of necking starts here, and you are getting a plastic failure here. This is the unload or reload this region, this much load it can resist. So beyond this load, you should not use it anywhere where you are applying your polymer to work. So this is semi-crystalline phase here, and this is amorphous region, starts elongating. Then the amorphous region goes on elongating the crystalline region, and finally, even the crystalline region starts arranging itself. It is no more compact like this, or has arranged itself like this. Here you see the networked case is here, then aligned cross-link case, and it becomes like these are the initial ones here, and this particular one, which is very hard and brittle polymer, which breaks here, and one is breaking here. So you can imagine there is a, like, even if you pull it, you apply stress on both the sides, you will not find elongation taking place here, because everything is completely cross-linked for this type of polymer. Okay, so that is what two different types of polymers has been compared. Then tensile response elastomer case. Elastomers, as I told you, एक छोटे से diagram में आपको बताया था, ये है आपका elastomer, rubbery polymer. Okay, along for a very small application of stress, this is the stress part, you are getting a huge change in strain. Okay, so the strain position is such high long, okay, on the x-axis, whereas stress applied is very small. So when for a small stress there is a long, huge stress strain, then they are the elastomers, and your hard and brittle polymer will be like this, and your thermoplast or plastic material will be like this, or they will be showing something like this. Same thing, stress strain behavior of polymer. Then polytetra fluoroethylene. I think you wrote a nice assignment on this. Okay, these are the properties of Teflon. Then coming to Bakelite, that is made from phenol and formaldehyde. This is phenol part. This is formaldehyde part. 1:3 ratio is used. You get such a molecule, which finally you get Bakelite formed. Okay, these are the properties, applications. Okay, so this is all regarding polymers. Okay. Now, is the screen visible to you? What do you have after this class?
Could you please second last slide?
Hmm?
Electrical,
आपका
electrical.
नेक्स्ट क्लास कौन सा है इसके बाद?
इलेक्ट्रिकल इंजीनियरिंग मैम.
ओके,
नाम टेक मैम.
इलेक्ट्रिकल थियरी क्लास. Who takes your electrical theory?
नाम टेक है सर.
Okay, so the class will be there.
Yes.
So I have to leave the class in time. Okay, so this part we will discuss tomorrow. Right, we have 10 minutes time. This part we will discuss tomorrow. Otherwise, tomorrow I would have given you off because what is your last teaching date? Your exam is starting from 12th.
Yes, ma'am.
Okay, so we have time. Next week also we can have the class. Okay, so no hurry of completing this portion. Okay.
You are not.
Yeah, this is an important diagram that you can note it down. And okay, you have a test on 28th and Vivas in the first week. So we keep the coordination chemistry part to be discussed later. Or we should complete the syllabus tomorrow. Only one small portion is remaining. Yes,
Complete tomorrow, ma'am.
complete tomorrow. Okay, so that then you can complete your file submission. File submission, I think tomorrow is the last date. And we will complete the coordination chemistry part. I think we will complete it in the month of March, not on 28th also. So we will meet sometime on Thursday and Friday we will have class. Monday's class I will not take. Tomorrow's and Monday's class, because that will give me like some time to communicate with you if there is any discrepancy in your file submitted, because that will be like the marks and all will be uploaded. So the first and the second part will be done, and your 28th का आपका test का result भी आ जाएगा. Then if anyone is absent and not submitting things, I'll be able to talk to you people. Okay. So let us have a class on Thursday and Friday, 3rd and 4th of March. Okay. So if you have any difficulty, that can also be discussed. Clear? Okay. So we will like have a class, theory class now on 3rd of March. Okay.
Okay, ma'am.
Yeah. And the time for your practical examination test will be put on your WhatsApp group. Okay. So that time you have to join, you will get the link and you have to write your test.